every living being needs to fight off other living beings that want to feast on them. So as multicellular life evolved over billions of years, it came up with ways to defend itself. Today, humans have a sophisticated defense network, like physical barriers, defense cells, and weapons factories. But one of the most important defenses of our body is largely unknown: the complement system. It evolved over 700 million years ago and is an army of over 30 different proteins that work together in a complex and elegant dance to stop intruders. All in all, about 15 quintillion of them are saturating every fluid in your body right now. Guided by nothing but chemistry, these proteins are one of the most effective weapons we have against invaders. Many other parts of the immune system are just tools to activate the complement system. But it's also really dangerous. Imagine having trillions of little bombs inside your blood that could go off at any moment. So our cells use numerous mechanisms to prevent complement from accidentally attacking them. Okay, what exactly does it do, and what makes it so dangerous? In a nutshell, the complement system does three things. It cripples enemies, it activates the immune system, and it rips holes in things until they die. But how? After all, these are mindless proteins randomly drifting around without will or direction. Well, this is actually part of the strategy. Complement proteins float around in a sort of passive mode. They do nothing until they get activated and change their shape. In the world of proteins, your shape determines what you can and cannot do, because shape determines what you can interact with and in what way. For example, in your passive shape you might do nothing. In your active shape, however, you might, for example, change the shape of other proteins, activating them so they can activate others. Mechanisms like this one can start cascades that spread very quickly. Imagine the complement proteins as being like millions of matches very close together. Once one catches fire, it ignites the ones around it. They ignite more, and suddenly you have a big fire. To show the actual mechanisms of the complement system is a tad complicated and overwhelming, so we'll simplify here. Now let's imagine you cut yourself and a bunch of bacteria enter the wound and make it into the surrounding tissue. Our complement attack begins with C3. C3 is the first match, the initial spark that will start our fire. And to do that, C3 needs to switch from passive to active. How this happens is complex, but let's just say it can happen randomly through other complement proteins that bind to enemies or through antibodies. All you really need to know is that C3 breaks into two smaller proteins, C3a and C3b, that are now activated. One of these parts, the C3b protein, is like a seeker missile specialized in bacteria, fungi, and viruses. It has a fraction of a second to find a victim, or it will be neutralized by water molecules. If C3b does find a target, it anchors itself very tightly to its surface and doesn't let go. By doing so, the protein changes its shape again. In its new shape, it's now able to grab other proteins and start a small cascade, changing its shape multiple times, adding other complement proteins to itself. Finally, it transforms itself into a recruiting platform known as C3 Convertis. This platform is an expert at activating more C3 proteins that start the whole cycle anew. An amplification loop begins. Soon, thousands of proteins cover the bacteria. For the bacteria, this is very bad. It can cripple the bacteria and make them helpless or slow them down. Imagine being covered by thousands of flies. But there's more. Do you remember the other part of C3, the C3a protein? C3a is like a distress beacon. Thousands of them flood away from the site of battle, screaming for attention. Passive immune cells notice the C3a proteins and awaken from their slumber to follow the protein tracks to the site of infection. The more alarm proteins they encounter, the more aggressive they get. This way, complement guides reinforcements exactly to the place where they're needed the most. So far, the complement has slowed down the invaders and called for help. Now, it's beginning to actively help to kill the enemy. The first immune cells to arrive at the battlefield are phagocytes. which means cells that swallow you whole trap you in a tiny prison and then kill you with acid. But to swallow an enemy, they need to grab it first, which is not easy because bacteria prefer not to be grabbed and are sort of slippery. But now the complement that has anchored itself to the bacteria acts as a sort of glue that makes it easy for the immune cells to catch their victims. But it gets even better. Imagine being covered in flies again. Now, imagine them turning into wasps. Another cascade is about to begin. On the surface of the bacteria, the C3 recruitment platform changes its shape again and begins to recruit new proteins. Together, they begin the construction of a bigger structure, a membrane attack complex. Piece by piece, new proteins, shaped like long spears, anchor themselves deep into the bacteria's membranes, until they rip a hole into them that can't be closed again. Fluids rush into the bacteria and their insides spill out. They bleed to death. The remaining bacteria are maimed and distracted by the complement and quickly taken care of by the arriving immune cells. The invasion has been nipped in the bud before it had the opportunity to become dangerous. You probably didn't even notice it. But while bacteria are not happy about complement, the enemies it might be the most useful against are actually viruses. Viruses have one problem: they need to travel from cell to cell. Outside of cells, they're basically hoping to randomly bump against a cell to infect by pure chance. Here, they're completely defenseless. And here, complement is able to intercept and cripple them so they become harmless and guide the immune system to devour them. Without complement, virus infections would be a lot more deadly. But wait, if we have such an effective weapon, why do we ever get sick? The problem is that in a war, both sides adapt. For example, when the vaccinia virus infects a cell, it forces it to produce a protein that shuts complement activation down. This way, the virus creates safe zones around the cells it infects. When it kills them and tries to infect more, it has a higher chance of being successful. Or some bacteria, for example, can grab certain molecules from the blood that keep the complement system calm and make themselves invisible. So the complement system, while being extremely important, is only one player in the complex and beautiful organization that is our immune system. A beautiful example of how many mindless things can do smart things together.